we're focusing on research around resilience, making buildings more resilient, making buildings that are better performing, so that not only can we address life safety still, but that after a big earthquake, people can go back to the buildings and they can resume their lives much quicker. We've learned a lot from the New Zealand earthquake. Buildings in New Zealand performed well. They performed well to code. Even though they performed well, people had to evacuate, buildings had to be demolished, and the reconstruction of the buildings, reconstruction of the social fabric of Christchurch has really taken a toll, and it's been really, really slow.
We saw after the Christchurch sequence in New Zealand that the buildings behaved exactly as they were intended to, and almost all had to be demolished after the event.
Conventional design philosophy is to have life safety in terms of seismic design. That means during an earthquake, your building will sustain some damage, but will not fall down, and it will provide for a means of egress for the inhabitants. So the building will be standing, but not structurally sound.
So for example, for reinforced concrete walls, we could have large cracks along the wall. We could have areas of the wall that's being crumbled, that's crushing. Maybe we even have to demolish the building. But people can leave the building safely. The buildings we're designing today with mass timber, we're typically using mass timber for columns, for beams, for floor slabs. But our lateral resisting systems, our walls, our elevator shafts, those are reinforced concrete or steel. And that's because that's what we have in the codes, so we can design for those, and we can, have buildings that perform to code, perform well for life safety, but are still not quite resilient and sufficiently, where we would like to go with our next generation buildings.
But with the resilient design, what our final objective is, to have those buildings back functional to its original functionality within a matter of a few days or a few weeks rather than a few months, or maybe in some cases the building has to be torn down because it had sustained a lot of damage.
So as we're innovating, as we're designing for new, better lateral resisting systems, we can go and start thinking about how to replace that reinforced concrete core with a mass timber system.
So we're really leveraging the mass timber as like a relatively stiff material, and then we're hybridizing that with some steel components to help us sort of get some stable energy dissipation. So the mass timber is really the portion that's engaging the entire building, and then we just have a little bit of steel that's sort of helping us out.
Specially detailed steel connections that allow us to dissipate the energy and essentially work as a structural fuse, that after an earthquake, just like in any fuse, you can go in, swap it out, and put in a new fuse, and the building is back to operation.
So this building is all veneer based, be it laminated veneer lumber or mass ply panels. These are products that are made by local manufacturers. So it's all Oregon fiber, and we are trying to come up with innovative design solutions with these newer products in the market.
Sort of the end goal, we want sort of the freedom to design low risk, well performing buildings. But to get to that innovation, you need to have very robust experimental data. You have to have numerical models that are very well validated from that experimental data. And again, you need these design methodologies that are going to be, they're going to work in the end.
These are expensive tests which not many places have the infrastructure to do or the capacity to do, but we are one of the few unique labs around the country that can test a 3-story building inside.
These sort of large-scale tests like this are just one step along that end goal of lowering the barrier to mass timber structures.
Yes, this testing coupled with other testing that we have been part of or some other teams are doing, they will all form a library of solutions. And those solutions will help increase the recognition of mass timber as a resilient material and system. And this will increase the acceptance of mass timber, not only in high seismic area, but also beyond them.
And so you're able to sort of hit sustainability, resiliency, and aesthetic value all in one material.
We hope that with our new solutions, with mass timber, we can have more resilient, more sustainable buildings, that after big earthquakes, communities can bounce back quicker and better.
We're hoping to really decrease that time so that we don't have to completely rebuild our city. We can, again, just re-inhabit it.